Hi, my name is Olivia McNally, and my presentation today will be on leveraging machine learning for solubility of new redox molecules, specifically TEMPO and its derivatives. So then on this slide, I have sort of some of the background information and kind of why we're interested in redox active molecules particularly. And that's because we're interested in using them in redox flow batteries. And redox flow batteries work by using redox couple solutions that are completely soluble within their half cells. So accurately predicting the solubility of these couples will maximize the energy storage of the batteries. And then I've also listed here the Hansen solubility parameters, which are sort of like descriptors of the interactions within molecules, and these offer a way to predict behaviors of a molecule. So not just solubility for our purposes, but also dispersion and diffusion and things like that. And this is a more accurate way of predicting these things than, say, the expression that you've probably heard before, like dissolves like, which looks at only polarity. So the overall goal of this program was to create a solubility model. And to achieve that goal, we were going to be collecting a bunch of data and then trying to draw conclusions from that data. And I go into more detail about the rough kind of outline of this process in a few slides, beginning on slide 5. But in addition to the overall goal and kind of end product that we wanted, there were also many new skills that I'd be acquiring, such as familiarity with Gaussian, as well as an introduction to data science and to Python. On this slide, I've included many different images of my redox active molecule, TEMPO, as well as of its derivatives. And the 4 images to the right of the slide were the images that I actually started the project with. The first 2 rows of those show TEMPO molecules with various hydrogen bonding patterns and alkyl chain lengths. And then the bottom 2 rows of that, the molecules in color, show molecules with different cations and counterions. And then in the center, those 6 images were the main molecules that I focused on sourcing data for. And sort of just in general, TEMPO is an interesting molecule and can be useful in redox flow batteries because it has a hard time reacting with itself, and that's due to the steric hindrance around that oxygen. So that oxygen connected to the nitrogen connected to the 4 methyl groups. On this slide, I have a rough breakdown of, for our purposes, the important pieces of Gaussian. And so we needed to input a .xyz file in order for it to give us a .log output file. And in that output file, there was a lot of information that had been computed, and we were mostly interested in the HOMO-LUMO gap data, as well as the dipole and multipole moments, the polarizability, the electronic spatial extent, and the rotational constants. And then on this slide, I've provided some visuals of the steps of our Gaussian process. And as I mentioned, we needed to have an input file in the format of the XYZ coordinates. So these coordinates were primarily generated using the Entos Envision software, which required us to enter a molecule's SMILES classification, and then it would generate the molecule for us. And then the site had the export option for exporting as a .xyz. So in the top left corner, I've included a picture of what the Entos Envision site interface looks like. And for the purposes of this slide, I chose to use benzene as an example. It was both one of the first molecules we successfully ran in Gaussian, as well as one of the simplest. And then in the bottom of the page, there is a screenshot of what the input file looks like. And so this is the exported XYZ file from Entos Envision, and then with a few additions made to it. So at the top line, that denotes the level of frequency, the level of theory, we were running at. And then the 0, 1 represents the charge and multiplicity of the molecule. And then from this, we were able to generate our output files. So in the top right corner now, I've included a screenshot of a part of the output file. It covers a lot of the information we were after. So from top to bottom, we have the electronic spatial extent, the dipole moment, and the multipole moments. And then by repeating the steps that I had just listed, we collected the data for 20 solvents, and we collected the data for 20 known solvents so that we could use the known data as a point of comparison to our generated and collected data. So on the left of the image is the known data that we were comparing to, and our collected data is on the right. Once we had a decently sized set of data with the known solvents, we were confident with using Gaussian, and we went ahead and began to run the redox active molecules as well as some of its derivatives. So here I've included a screenshot of the output file for neutral TEMPO, and at the bottom of the page you can see the data that we had started collecting. So new to these molecules were the beta HOMO-LUMO gap data that we were now collecting as well. So the next big part of the project was going to use both Python and data science skills. And in order to use those, I needed an introduction to both. And a lot of that came from the Python Data Science Handbook. And so I've included an image from this handbook on the slide, which helps to give a better idea of what data science is, which is described as the crossover of hacking skills, math and statistics knowledge, and substantive expertise. And we wanted to use these skills to generate multivariable regressions, which are regressions that have a single dependent variable and two or more independent variables. And recall that our goal for this project was to create a solubility prediction. So this means that the Hansen solubility parameters would need to be the dependent variables for each regression. So to get started with the regressions, we began with single variable regressions or linear regressions to help familiarize ourselves with not only the data but the graphs as well. And you can see from these that the R-squared values are not great, which was actually expected. So once we felt comfortable with this, we went ahead and began our multivariable regressions. And so once we'd moved into multivariable regressions, you can see that they look a little different because there are too many variables to have them displayed in the same type of graphs as the linear regressions. So here now we're interested in the calculated coefficients, which then become parts of the equations, and the R-squared values. So all of the regressions and calculations and statistics were done using the data analysis tool pack in Microsoft Excel. And then this slide just shows the R-squared values and the equations that were listed on the previous slide. I just pared down the screenshots a little bit. And so you can see from these that the R-squared values are better than they were for the linear regression, but still not great. And so we wanted to figure out sort of how we could make those better. And one of our solutions to try and improve the R-squared values was to normalize the data. So normalizing the data means that you use kind of the observed or expected maximums and minimums of your data set to generate numbers that all fall between a 0 and a 1. So the original data is on the left, and then the new normalized data is on the right. And you can see that all those values fall between a 0 and a 1. With the normalized data, I recalculated the regression statistics and coefficients, and as you can see, received a much better R-squared value. So I've included the regression stats from the unnormalized data at the top right of the slide for easier comparison. And I'd also like to note that these regressions were done with the addition of molar mass and dipole as two new independent variables, but the R-squared of these regressions with the additional data prior to being normalized, calculated with the other unnormalized data, still gave similar R-squared values to those at the top. Using the regression equations with the improved R-squared values, I found the dispersion, polar, and hydrogen bonding parameters of tempo, hydroxy tempo, and amino tempo. And these values are shown in the image. They're highlighted in green, and these are the calculated Hansen solubility parameters for these three molecules. So in other words, the calculated results from the solubility model. So for next steps, I would like to continue to calculate the parameters for more tempo derivatives, and importantly also is validating the parameters, which is just going to be getting that confirmation that the solubility model is outputting accurate predictions. And there are also changes that could be made to the regressions. I could run new regressions with the addition of new variables such as molecular fingerprints, which is something that I started working on this last week. And I've included an image to the right of the slide of the code that I've been using for that, as well as polarizability, which takes significantly longer to run the level of theory with frequencies, which is what reports the polarizability. So it wasn't recorded for all of the molecules, so I'd like to rerun all of them and include the frequencies just to get that data. Thanks so much for watching.